Hi there, my name is Ms. Midha, and today we're going to be focusing on the following question. How do we use the Pythagorean identity to identify points on the unit circle? Now, before we get into this whole what is the Pythagorean identity, let's go ahead and take a step back and review how to find coordinates of a point on our unit circle. So we're going to take a look at this first example right here. All right, I'm given a unit circle. And I know that it's a unit circle because it says that below is a circle centered at 0, 0, the origin, with a radius of 1. What we need to do is figure out what are the x coordinates of P if P is rotated counterclockwise pi over 3 radians from the point 1, 0. So here's my point 1, 0, and P has been rotated counterclockwise pi over 3 radians from that point 1, 0. Okay. So what I'm going to ask you to do is pause the video for as long as you need and see if you can figure out how to solve this on your own. Once you think you have it, go ahead and unpause the video and we will continue. Okay, so if I look at this diagram and I think back to previous lessons, I'm remembering that in order to figure out these coordinates for P, what we needed to do was draw a right triangle, right? So we basically needed to create a height from point P down to the x-axis. And this created our right triangle with points at the origin, point at P, and also a point on the x-axis directly below P. Okay, now, what other information do I know? Well, I know that the radius is 1. So that means that our hypotenuse is also going to be 1. Okay, I also know that whenever we write a coordinate, we write it as x comma y. So if I can take a look at this triangle and see if we can figure out, what's my x, what's my y, that might help me get to my final answer for this problem. So if I look at the side that is opposite of theta, and remember theta, I'll write it on the left corner here. Theta, it's a Greek letter, and it's often used in mathematics to denote an angle. So you're going to see that theta symbol a lot throughout this unit. Okay. So if I look at the side that is directly opposite of theta, so the one that's in red right now, I know that the length of that side, again, the side that is opposite of theta, that's going to be the same as my y coordinate, right? The side length opposite of theta is the same as what my y coordinate will be. I also know that the side adjacent to theta, so the horizontal side in this case, and I'll shade it in blue, that's going to be x. Okay, so now what? Well, I have a right triangle. I'm given a side length. I know my hypotenuse. I'm given one side length. And I also know an angle measurement, right? I know theta. So knowing that information and thinking back to, previous courses, I know that x is going to be the same thing as cosine of theta. And I also know that y is going to be the same thing as sine theta. Well, so now what does that do? That will actually allow me to figure out what my exact coordinate of P is, because I also know what theta is, right? Pi over 3, they're giving me that. They're telling me that pi over 3 is the angle that was created after P was rotated counterclockwise. And so that means that pi over 3 is theta. So now I'm actually able to write my coordinate for P. So my exact coordinates are going to be cosine. Now again, it's cosine theta. In this case, theta is pi over 3. So cosine of pi over 3, sine of pi over 3. Now those are my exact coordinates. Okay. And what if we wanted to figure out the approximate coordinates, right? These are the exact coordinates. But what if I wanted to know, the approximate coordinates? What would I have to do? Well, all that we'd have to do here is just put both cosine pi over 3 and sine pi over 3 into our calculator and see what we get, right? So I encourage you to do this. If you have a scientific calculator or if you have a graphing calculator, make sure your mode is set to radians and then try it out, right? Type in cosine of pi over 3. What should you get? You should get 0.5. And then when you type in sine pi over 3, you should get 0.875. So again, this first line, these are my exact coordinates. And then the next line, these are my approximate coordinates. Okay, Now, something that's kind of interesting to note, just in terms of the difference between exact and approximate, we know that approximate we're rounding, right? We had to round that sine of pi over 3, whatever we got in the calculator, we had to round it because there were so many numbers. And what's interesting is that if you actually sort of look at this through a different lens, you'll actually be able to see even more so why that's the approximate, those are the approximate coordinates. Okay, so what am I talking about? Well, if I take my x and my y coordinates, both for exact and both for approximate, and I put it back on the right triangle, right? Because again, the right triangle had my y and had my x. I knew that y was a sine of theta. I knew my x was a sine of theta. And so I'm just going to go ahead and draw the right triangle down here, just separately. But if I know that these coordinates correspond to the side lengths on my right triangle, and I pretty much just sort of plug them in, I'll actually plug in 0.5, I'll plug in 0.875 there, and I'll plug in 0.5 over here. Now, if I want to sort of see how this is approximate, I can actually apply the Pythagorean theorem here, okay? And what happens is this. Technically, the Pythagorean theorem is a squared plus b squared equals c squared. But if I use my approximate coordinates and I do 0.5 squared plus 0.875 squared, I end up getting an answer that's slightly larger than 1 squared. And I encourage you to try this out and see and notice, right? It's not exactly equal to 1 squared, aka it's not equal to 1. But if I were to plug in my exact coordinates, and it would be cosine squared pi over 3 plus sine squared pi over 3, what would happen is that I actually would get an answer that is exactly equal to 1 squared, or 1. So again, just sort of kind of noticing the difference between exact coordinates and approximate coordinates. This will come in handy as you move along throughout this unit. Okay, let's look at another example. I want you to keep this idea of Pythagorean theorem in your mind, by the way, and I want you to keep this idea of what we just talked about how to find our coordinates on an actual coordinate plane. Okay, so we have a new example now, still the same unit circle, but now instead of finding the point, now we actually have to verify if this point is in fact on a unit circle. So let's think this through. How would we figure out that point negative 0.5 comma sine 4 pi over 3? How are we going to figure out whether this is on the circle or not? Well, we want to actually think about putting in another right triangle, right? Because if I think about putting in this other right triangle, or if I think about a right triangle within my unit circle, it helps me to visualize where this point would be. So negative 0.5 sine pi, 4 pi over 3, I know it might be here. Again, we don't actually know if this is on the unit circle. But again, if I sort of draw in my right triangle, I can sort of think about what's going on here, what my x coordinate would be, what my y coordinate would be in the context of a right triangle. And it also helps to remind us about the actual equation for a unit circle, right? What is the equation for a unit circle? Well, the equation for a unit circle was x squared plus y squared is equal to 1, right? Very similar to like when we had the x and the y on our right triangle, we could look at it in terms of like the Pythagorean theorem almost and notice that it's pretty similar to that. So if x squared plus y equals 1 is the equation of our unit circle, what we can actually do is plug these points into our x and our y and see if in fact the equation is true. Will negative 0.5 squared plus sine squared 4 pi over 3 actually equal 1? And when you do that, I'll just write it out real quick. So negative 0.5 squared plus sine squared 4 pi over 3. Be mindful, by the way, of where you put that squared when it comes to writing, sine squared, cosine squared, anything like that. Okay, so negative 0.5 squared plus sine squared 4 pi over 3. When you plug that into the calculator, you actually do get 1. So what does that mean? That means that is this point negative 0.5 comma sine 4 pi over 3 on the circle? Absolutely, absolutely. Because again, all points on the circle make x squared plus y squared equal 1 true, and negative 0.5 squared plus sine squared 4 pi over 3 rather, it is in fact equal to 1, so it is on our unit circle. Okay, what about this one? Try it out, pause the video, right? Try it out and see if the point negative 0.5 comma sine 5 pi over 6 is on the unit circle. I will tell you that this one is not going to be on the unit circle, because when you plug in negative 0.5 squared plus sine 5 pi over 6 squared into the calculator, it does not equal 1, right? Sine 5 pi over 6, that has a value of 0.5. And so the point negative 0.5 comma 0.5 is not on the unit circle, right? It doesn't make the equation x squared plus y squared equal 1 true. Okay, one more example. Suppose that sine theta equals negative 0.5, and that is in quadrant 4. What is the exact value of cosine theta? All right, think about this one. Again, pause the video, think about it for as long as you need. Now, quadrant 4, right? Again, we're trying to figure out if we have a sine theta equal to negative 0.5 and it's in quadrant 4, what is the exact value of cosine theta? So, right triangle again, right? Draw in that right triangle. It always helps to visualize what's going on if we know where that right triangle is. So I have quadrant 4. I'm going to go ahead and draw that radius in first, which will become our hypotenuse in a moment. So when we draw in our right triangle in quadrant 4, okay, we'll again notice that our hypotenuse is 1. We will notice that our horizontal side, right, our horizontal side is 0.5. And our vertical side is x, because that's what we're looking for, right? Our side that is vertical or adjacent to our angle measurement of theta, that's going to be x. Okay, so now how do we solve this? Well, we go back to that Pythagorean theorem. So we've got x squared plus 0.5 squared is equal to 1 squared. This is the equation to figure out what the exact coordinate of cosine theta is, right? Because this based on the Pythagorean theorem, this must be true. So I encourage you to do the math on this. I will tell you right now that after solving it, you will get x is equal to the square root of 1 minus 0.25. Right? You might also write this as x is equal to 0.7 x is equal to the square root of 0.75, and so that tells me that the cosine of theta is equal to the square root of 0.75. Okay, so I'm going to leave this up for a few moments, but I want us to sort of think about a new question. We've been looking at, different points on the unit circle, figuring out whether they are on the unit circle or figuring out what the points on the unit circle are. And we keep going back to this idea of Pythagorean theorem. We keep going back to this idea of the equation for a unit circle, x squared plus y squared equals 1. And we keep going back to this idea that x is equal to cosine squared and y is equal to sine squared. So here's my next question. I'm going to actually turn to the next slide so we can look at it just, on a clean page. If theta is an angle on the unit circle, if theta is an angle on the unit circle, what is the value of cosine squared theta plus sine squared theta? And think about this for a moment. Pause the video again for as long as you need. Think about the fact that we already know that x squared plus y squared is equal to 1 squared, right? That's our unit circle equation. We already know that we had to draw in right triangles and learn that x is the same thing as cosine theta, that y is the same thing as sine theta. So thinking about all those ideas, what is the value of cosine squared theta plus sine squared theta? Well, all points, x comma y, on the unit circle, they make the equation of the circle x squared plus y squared equals 1 squared true. So that tells me that the cosine squared theta plus sine squared theta is going to equal 1, right? Why is that? Again, because x is equal to cosine theta, y is equal to sine theta, right? And so for a point x comma y in a unit circle, and I'll just go ahead and draw one in, right? Let's just say that's our point x comma y in the unit circle. We can draw in our right triangle. We can draw in our right triangle with the leg of length cosine theta and sine theta, or the absolute value of cosine theta and the absolute value of sine theta, and the hypotenuse 1. Cosine theta, sine theta, and our hypotenuse 1. So by the Pythagorean theorem, we know that cosine squared theta, I'll write it one more time over here, cosine squared theta plus sine squared theta does in fact equal to 1. So this right here, this is what we call the Pythagorean identity. Cosine squared theta plus sine squared theta is equal to 1. And this identity, right, cosine squared theta plus sine squared theta equals 1, this is where theta is an angle on the unit circle. So just keep that in mind. And also just another reminder, right, what are identities? Identities are equations that are true for all values of the variables in them. So in addition to determining if points are or are not on the unit circle, what's cool about the Pythagorean identity is that it can be used to, for example, calculate the value of the sine of an angle from the value of the cosine of an angle. So that's something that you'll see in future lessons, but it's kind of really nice to know what this identity is used for. All right, so to summarize, let's say we have a point P, that point P again, but this time our coordinates will be A comma B, given this illustration. So the coordinates are A, B, and it's on the point P is on the unit circle, like we see here. All right, so using the Pythagorean theorem, we know that A squared plus B squared equals 1. We also know this is true using the equation for our unit circle with radius 1. So that's x squared plus y squared equals 1 squared or 1, which is true for the point A comma B since it's on the circle. And we also learned that another way to write the coordinates of P is by using angle theta, right? Which gives us the location of P on the unit circle relative to the point 1 comma 0. So when we think of P this way, we know its coordinates are going to end up being cosine theta comma sine theta. And since A is equal to cosine theta and B is equal to sine theta, we can return to the Pythagorean theorem and actually say that the cosine squared theta plus sine squared theta is in fact equal to 1. So again, that is true for all values of theta defined on the unit circle, and it is known as the Pythagorean identity.